Yeah, so I'm going to talk about ODYSEA, which is proposed to NASA as an Earth System Explorer. It's a joint proposal with NASA or JPL working on it and the French Space Agency CNES. So it has a large international science team. And really, when we talk about measuring winds and currents from space, we're thinking about how the ocean and atmosphere communicate with each other. So you can think about hurricanes Idalia and Franklin shown in this image, or any number of other weather events. There we go. Okay. And what we know really is that the ocean drives disruptive weather. That applies to atmospheric rivers, it applies to hurricanes, it applies to heat waves. I think it even applies to this enormous winter storm Blair that is sweeping across the US at the moment. We need massive amounts of moist air drive these systems. And so really understanding how the ocean and atmosphere communicate is critical to that. That emphasis on ocean atmosphere communication has been brought out in the community. So in the Ocean Ops 19, the oceanography exercise to identify community priorities, there were numerous community papers that documented the importance of air-sea interaction in one way or another. And that led to the formation of ODYSEA, the Observing Air-Sea Interaction Strategy Working Group, which then went through and synthesized all these community papers and grouped them into three grand ideas. So grand idea number one, let's see, can you see my mouse here? Yeah, is looking at the need for in situ observations across the globe to look at air-sea fluxes. Grand idea number two looks at knitting those together with satellite data optimized to measure air-sea fluxes. Grand idea number three asks about improving models and the understanding of air-sea interaction processes. And then there's some umbrella themes that overarch these related to the availability of data, fair data principles, equity. So all important things. Today, we're really talking about grand idea number two, how to get satellites to give us global information about air-sea fluxes. And so ODYSEA is directed directly at this. And what I'm going to talk about today in this quick talk are really what are the knowledge gaps that motivate ODYSEA specifically? How does ODYSEA address these gaps, and how does the instrument work, and what the status of the mission is and how you can be involved. Jimbo was just pointing out to me there's a broader question for PAS in thinking about the next decadal survey where NASA plans out, or NASA is directed to on what they should do in the next decade, and that's something else we can talk about. So when we think about measuring air-sea fluxes from space, there are a lot of ways to think about it. There are different types of fluxes. So we can think about momentum fluxes, where the wind loses or gains strength from the upper ocean. That's thinking about wind stress, wind work. We can think about heat fluxes as radiative or sensible heat fluxes, freshwater fluxes, precipitation and evaporation, or gas exchange. ODYSEA is really driving at this momentum flux. It's measuring winds and currents so that we can look at wind stress, which depends on the difference in atmosphere and ocean surface, or ocean speeds and wind work. But wind permeates all of these. And so everything in red has a wind link. If we were thinking about heat fluxes, the butterfly concept, which was proposed as an Earth Ventures mission and reviewed well but was not selected, was aimed at getting at turbulent heat fluxes, sensible and latent heat fluxes. And that ties into latent heat flux ties into evaporation, so that had direct links to freshwater. And gas exchange also depends on wind, and the Zephyr proposal, which was just to get winds, a high resolution scatterometer proposal, was also aimed at getting the information you need to get better gas exchange just by getting at better winds. So winds permeate all of this, and that really underscores the importance of looking at vector winds closely if you want to get at any of the flux quantities. So if we're thinking about ODYSEA, which is aimed at measuring winds and currents together, So you can imagine having a measurement that sweeps over the entire globe. Then what do you do? And the ODYSEA proposal is focused on 2 science objectives and 1 application subjective. And just to be quick, I'm going to give you a quick overview of some of the highlights of that. So first, on the application side, we measure winds from space at the moment. There are a number of missions in the works. So if you look in the 2030 timeframe, for example, India plans to run a scatterometer OceanSat with a noon and midnight timeframe. The European scatterometers are targeting 9:30 a.m. and 9:30 p.m. That's ASCAT and its successors. And then there's Harmony, which is a very high resolution SAR-based system that will measure a tiny fraction of the world in the 6 a.m., 6 p.m. time slot, and passive instruments from European SIMR and the US WSFM at the 6 a.m. and 6 p.m. time slot. These are sun-synchronous orbits, so they really only measure at one time of day. And what you see in this is that there's a big gap from midnight to 6 a.m. and from noon to 6 p.m. when there are no vector wind measurements in the works. And so ODYSEA is targeting 4 a.m. and 4 p.m. It's trying to get as close to the middle of that gap as we can without hitting some difficult orbit things. And that's really important for operational needs to just give the information that's needed to watch evolving storm systems and to look at diurnal variability. But ODYSEA is also aimed at measuring winds and currents together. That's something we've never had before. And there are big gaps in our understanding about this. So just to put a framework in this, you can imagine winds, shown as these yellow vectors, blowing over an eddy, which is this blue circle with the arrows. And you can see on the north side of the eddy here, the winds are blowing counter to the currents. And so that leads to a stronger wind stress. The wind relative to the currents is really strong, and that puts or exerts more stress on the ocean than on the south side of the eddy, where the winds and currents are in the same direction. And so they're moving in the same direction. There's less apparent wind driving the ocean. And that leads to some thoughts. First of all, if the only way we ever measured winds was from satellites always measure wind relative to currents. They measure effectively something that's like wind stress. And so we could ignore relative winds. But in reality, we calibrate our satellites by using moorings or in situ measurements that are measuring absolute winds. And so we actually need to know these 3 components, the winds, the currents, and the wind relative to the currents, in order to pull apart all the things that we need to understand how winds drive the ocean. And so if we can unravel that, there's a lot we can learn. We know in the upper panel here that wind stress curl induces motion in the atmospheric boundary layer. So depending on the sign of wind stress curl, you can have upward or downward motion. And then you can imagine that that's modified as winds pass over currents. There are different views of this. So here the wind is shown as this purple vector. It's going over a current, which are these white vectors. If you look at the published literature, there are 3 hypotheses in the works. Some studies say wind and currents, there's really no response, no impact of winds on induced vertical motion. So maybe that's not plausible. Some studies say that there is an induced response that is local. So there's a local response directly over the currents. You see an induced vertical motion, but nothing anywhere else. And a third category of studies show a local and remote response. And so clearly we need more information in order to tease this apart, and ODYSEA is set up to get that. The second thing we can think about for ODYSEA is that we've actually never really measured currents globally in any useful way, and certainly not upper ocean currents that include the ageostrophic component. So we have a lot to learn then about how winds respond, or how currents respond to different environmental conditions, different winds and different mixed layer depths. If you look at the climate literature, it shows one set of things. So climate literature says in a warming world, the mixed layer is likely to get shallower. That will trap the currents in the upper ocean, and the momentum will transfer more easily, and we'll get faster currents. So climate models show this. With a deeper mixed layer, you get weaker currents. And that makes a lot of sense. It's well validated in models. The challenge is it doesn't actually work when you get to small scale processes. So if you look at a model that resolves some mesoscale processes, as this Rocha et al. Study does in the Curcio extension, you see that at the end of winter, when the mixed layers should be deep, you see much more energetic systems than you do at the end of summer when the mixed layer is shallow. It's the opposite of the climate model scenario. And the explanation for this is that in winter with a deeper mixed layer, you can store more available potential energy that is more easily released into kinetic energy. So that's shown here schematically. The summer conditions have the shallow mixed layer, the winter conditions have the deep mixed layer, and the deep mixed layer gives you more eddy kinetic energy. These differences between the climate scenario and the submesoscale scenario really underscore our need for more global observations to understand how these two different mechanisms work and when you transition from one to the other. So ODYSEA is set up to address these by providing winds and currents simultaneously with 5-kilometer postings across a 1,500-kilometer wide swath. As I said, it's an Earth System Explorer proposal to NASA. It has strong support from CNES and from the US Space Force. And the goal is to get more or less daily coverage of most of the planet with near real-time data. So this is a first ever mission. We've never had total surface currents. It's certainly not simultaneous with winds. So I want to talk a little about what we're actually measuring. And the starting point for any wind measurements from space is capillary waves. If you blow wind over water, you get capillary waves. They're little waves, finger-sized waves, and they have the virtue that their crests are more or less perpendicular to the wind. So if you send a radar signal down to the ocean surface, you get backscatter off the surface. If there's no wind, you get a mirror reflection and nothing comes back to the satellite. But we normally have wind, and so we have capillary waves, and so there's backscattered energy in all directions. The backscatter has a Bragg scattering effect, and so the different amounts of energy come back to the satellite depending on the orientation of the wave crests of the wind relative to the satellite track. So you can see for 16 meter per second winds in this plot, you get really different amounts of backscattered energy depending on the orientation of the satellite and the wave crests. So the concept in scatterometry is that you measure not once, but multiple times. So you get different amounts of backscattered energy from the same patch of ocean. And by looking at those together, you can figure out not just the wind speed, but also the direction. So ODYSEA does this sort of like QuickScat with a rotating pencil beam. QuickScat uses 2 beams. ODYSEA uses a Ka band, which allows much higher resolution. And so it does it with a single beam to get 5-kilometer resolution. So you have this satellite with this rotating beam. It's measuring looking forward, and then it flies over and it measures the same patch of ocean looking backwards. And so you get multiple looks at the same patch of ocean. And from that, you can determine the speed and direction. But ODYSEA goes one step further. It says, in addition to looking at the backscattered energy, we can also look at the phase of this radar signal. That's something we've never really done before. So if the ocean surface were stationary, the backscattered energy would just go uniformly out in all directions and you'd get uniform phase. But in fact, these capillary waves of the ocean surface are riding on top of the ocean currents. So they're coasting along with the ocean currents, and that means that the backscattered energy is Doppler shifted relative to, because of the moving ocean currents. It's also Doppler shifted as it's received by a moving satellite, but ODYSEA is intended to be precise enough that it can take out both the motion of the satellite and still get the information about the moving ocean surface. So by looking at this Doppler shifted signal, the change in the phasing of the radar backscatter, you can tell how fast the ocean surface is moving. Now, we're used to measuring ocean currents from altimetry, from geostrophy. So we get a pretty large scale, larger than the Rossby radius geostrophic estimate of currents. ODYSEA is looking at the total surface current. So it's getting geostrophic current plus the wind-driven component, the Ekman component, and anything that falls into this ageostrophic category to get the total surface current. So it's a different quantity, and there's a lot of excitement about being able to look at geostrophic currents and total currents at the same time. The concept for ODYSEA is not new. Ernesto Rodriguez first proposed the Doppler Scatterometer concept more than a decade ago. It went through NASA's Instrument Incubator program. An airborne system was built. The airborne system has been used as the basis for S-MODE, the submesoscale ocean dynamics experiment, which is an Earth Venture suborbital program. Suborbital means it's on an airplane, not on a satellite. And so ODYSEA is simply an effort to get this proven technology onto a satellite. It is intended to be completely transformative, and you can compare what ODYSEA can do in one day with what we get from other satellites. So here you can see ODYSEA in this sweet spot in the shaded purple, providing 5-kilometer wind resolution with about 80% daily global coverage, compared with what we get from QuickScat or 2 European ASCAT scatterometers or COVER. ODYSEA is providing much higher spatial resolution and much greater temporal resolution, much better temporal resolution than we get from a SAR-based system like Harmony, which will launch later in the decade from the Europeans, but is intended to get a very small fraction of the world, little postage stamp-sized areas. For currents, it's a similar story. At the moment, we get currents from geostrophic systems. Those give us a pretty coarse temporal resolution because of the revisit times. And we can argue about what the spatial resolution is from geostrophic currents. ODYSEA will be a game changer with the almost daily coverage and high resolution. So it will meet operational needs with near real-time winds and currents to let us look at the evolution of storms and surface wave propagation, maritime safety, debris transport, and it supports NOAA, the Navy, Coast Guard Search and Rescue, and on the international side, Mercator Océan International. You can see what ODYSEA will do. Here you can look at winds. We're looking at wind stress curl to look at gradients. That really shows what's going on. And you can see with ODYSEA, we can hope to bring into relief to really see the structure of wind stress curl in a way that we never have before. For currents, we have a very fuzzy view at the moment, and ODYSEA will show sharp filamented structures that we haven't seen in the past. So a quick mission overview. ODYSEA is filling an operational a void, both scientifically and operationally. We have no satellites that measure total surface currents. We have no US scatterometers, nothing that provides 5-kilometer postings. There are no sun synchronous measurements in the midnight to 6 a.m. range. So there are a lot of gaps to fill. It is planned for about a 600-kilometer orbit with 4 a.m. and 4 p.m. time of day, near real-time data. And it is, at the moment, as I said, one of 4 Earth system explorers that are currently going through further study. We're producing a concept study report. What that means is that the science has been reviewed. It's perceived as really great. And the goal for ODYSEA is to demonstrate that the scientific goals can be achieved on time and on budget. NASA expects to select 2 missions in, I guess they say November 2025. We'll hope that they're able to stick to that timeline, with launch dates expected for 2030 and 2032. So broadly speaking, how can you get involved? There are opportunities to test the science ideas using the ODYSEA simulator. So if you go to the ODYSEA website, you can link to the GitHub and get hold of the simulator, test out the data. If you do anything, we'd love to hear about what you do, what you find out, what works, and what you might want. If you have applications for which you want to be an early adopter or contribute, let us know. And if you want to join the broader discussion about air-sea fluxes from space, the OASIS webinar series for this runs Tuesdays at 8 a.m. Pacific time, 11 a.m. Eastern time. And you can sign up for that on the OASIS website, and you can also get access to a very large library of previous recordings. I think there are about 70. So that's what I have for today, and I am really happy to talk. A little summary slide for the end.
Yeah, great. Thank you, Sarah. It's very impressive. Can you tell us a little bit about how this satellite will function over ice-covered regions? And is it a polar orbit?
It's a polar orbiter, and so there will be measurements over ice. And scatterometers do return data over ice. So ice is not a science objective, a priority science objective for ODYSEA, but we do have ice people on the science team. Fanny Girard-Ardouin from Ifremer is part of the science team, and there is an intention to get an ice product that will A, identify when ice is present, and B, be able to look at some of the ice motion, ice properties. NASA also gives us an opportunity to do a science enhancement opportunity, and we are talking to ice people at JPL as well about building an ice product that will be available to both provide ice coverage and detailed information, the best information we can get from that.
Great, thank you.
All right, I see Jimbo's hand next.
Yeah, thanks, Elise. Thanks, Sarah. Two questions. The first one, I know that, to build a mission, you don't want to add a dependency to other things. But on the other hand, if we have, for example, for altimetry community, SWOT, we can use some synthetic data to demonstrate the synergy between SWOT and ODYSEA, for example. What do you think about that kind of activity, and what can the community do?
That's a really good question. Yeah, so we're obviously, ODYSEA has to be proposed as a standalone mission, as you said, but I think that there's a lot of interest in, well, A, continuing the existing constellation of nadir altimeters, and so there will be something to compare with, we expect, and also in looking at the potential future for swath altimetry in some form on the European side and the US side. So I think it's really worth asking the speculative questions. What could be done if we had both? Where are the gaps? What are the what would you expect to find? What are the observing system requirements?
Yeah. Okay. The second question is related. Does the project or the team have any plan to provide a simulated data set other than just a simulator, so that the community can use the standardized data set to compare the different algorithms,
much as we can in the GitHub, and if it's not, we'll bug Alex Hoynt and try and get something online.
Sorry, Sarah, I think we kind of have a lag. My question was whether we want to produce a data set instead of a simulator.
Yeah, I think there is a need for a data set, and I think that that's the goal as part of the simulator in the next few weeks, to get as much as possible available for the community.
Okay.
So there have been two simulators, one on the French side and one on the US side, and we've been trying to get everything coordinated so that they're readily available for people and so that we know what's being done with them. See a bunch of hands up. So.
All right, in the order of go, Hailong was next.
Hi. Yeah, thank you. Hi, Sarah. I wonder if the wind measurement has something to do with cloud. How about cloud covered areas? And also, is there any interference between the surface wind waves and like ship generated waves?
So those are good questions. Scatterometry is radar, and so it works through clouds. So there's no data loss from cloud cover. That's different from, say, PACE, which is looking at visual images and would lose data through clouds. Ka band, ODYSEA's radar band, does have interference from rain. And so we expect that we won't see in rain cells, but we'll see around them. And because of the very high resolution, I can even show this image, with the very high resolution allowed by Ka-band, we have a lot less rain dropout than you might get at 25-kilometer resolution. So that's what this image is showing, the WRF simulation. And you can see that at 4-kilometer rain flag, which is roughly what ODYSEA gets, you lose a lot less data than you do with a 25-kilometer rain flag. But that's not what you were asking. I mean, clouds are not an issue. And then you had a second question. I think.
Yeah, I was wondering when over the ship channels, ship corridors.
Yeah, so what a scatterometer does is to scatter off of waves that are roughly the size of the scatterometer signal, which is 1 centimeter. And so those are really wind waves, these capillary waves. And so we don't expect to see the sort of big wave signals due to ship wakes or swell. The scatterometry is really just this Bragg scattering off of small waves.
Great, thank you.
It's something to watch out for, I'm sure. There could be a little wrinkle that could be fun to look at.
All right. Up next, we have Ke.
Yes. Hi, Sarah. Thanks for the excellent presentation. Very informative. So sort of related to data coverage and quality, we talked about the Arctic Ocean. What I'm thinking is, how about coastal ocean, really close to the coastline? Do you envision any data coverage or quality issue at that interface, or do you think? Yeah.
Yeah,
Thanks.
that's a high priority for ODYSEA, actually, to get as close to the coast as possible. So with 5-kilometer resolution, you can imagine getting within 5 kilometers of the coast. Existing scatterometers have really large radar side lobes that interfere with data near the coast, and that will not be an issue for ODYSEA because of the small intrinsic footprint. So it will get close to the coast. We also have a plan to do again, a science enhancement opportunity, an additional budget request for NASA to do a high resolution wind product. So we're hoping that we'll be able to get funding to do a more experimental 1 or 2 kilometer product that will get even closer to the coast. But this will be a game changer for near coastal processes.
Excellent. Thank you very much.
All right, and we started a minute or two late, so I'm going to take some more questions. Mike, I see your hand up.
Thanks. Hi, Sarah. I have 2 questions actually. One first has to do with the in situ observing system that helps complement the current measurements from ODYSEA. Can you speak to those in situ networks that we have, say the surface drifter program, our current meters on our moored arrays, and their importance for ground truthing?
And I'm so glad you brought that up. Yeah, scatterometry relies on the existing observing system to ground truth data. So that's at the heart of what everybody does. And ODYSEA for surface currents will have a measurement that's not quite like anything that we're measuring at the moment, but nonetheless, we expect that to ground truth the data, we're going to look at everything that's available. So that includes moorings and surface drifters that are out. There's also a CalVal plan to deploy Carthay type surface drifters that are probably as close as possible to the surface measurement only that ODYSEA will get. But in situ measurements are really critical for validating, and the existing observing system is a really important part of that. So I don't know what people know about scatterometer calibration and validation, but people do something called triple collocation, where they just line up everything and try and get, if they have 3 things together, try and show that at least 2 of them consistently agree.
Great. And then the other question I had is regarding the broader community participation, to follow up on your final slide. We in the U.S. Climate Project Office can certainly include an item in an upcoming newsgram that'll reach over 3,000 subscribers. I know you also have a big subscription list, so there'll be overlap there, but just in terms of announcing to the broader community the availability of the archive and that they can pull in data on a test basis, right? To play with it. In terms of getting your feedback. So is that also, if you're an early adopter or you want to test science ideas, or even, is there ability to capture from the broader community their uptake or their participation in these activities in such a way that's beneficial to the decision-making process at NASA in moving forward in November?
I think so. I think that that's going to be important. So we face we have sort of 3 review steps coming forward. We produce a written document for April 17th, which is mostly about implementation. So the engineering is important. But NASA has moved towards really emphasizing Earth science to action. And so that's a priority that we'll address in the written document. Then we do a site visit, and again, that's mostly about implementation. We talk about building a spacecraft and have people who are dealing with exact instrument precision get interrogated by people who know a lot about radar and engineering. And then the final step is that the PIs for these 4 proposed missions show up at NASA headquarters and brief the selecting officials. And the selecting officials, that's Nikki Fox and Karen St. Germain, are interested in meeting societal needs. They report to people who care, who are in Washington, D.C. and care about what society needs. And so that means that through September, the information that we gather about societal needs, who's going to use this, and what the impact is going to be a really important part of the message.
And can you think of, and we can take this offline, how our program and the PAWS panel might be able to help marshal some of that input on the importance for societal use?
Yeah, I think there are a bunch of things that we can envision doing. One is that if people have the bandwidth to do an ODYSEA and to come up with something that says this would make this much difference in a prediction, we really want to hear about that. That's the sort of concrete number we can get. If there are more general statements, I mean, the baseline description of an ODYSEA is it costs too much to do them, and so people don't do them. They speculate about what they would do if they could. So just getting the sort of back of the envelope guesses about what an ODYSEA would show is also going to be important. And I think there's also there's some moving targets in this. I was just emailing Jimbo today because I was reading Nature, and there's a paper that just came out about machine learning for weather forecasting. And I'm thinking, if we're making a case that we need this information, we're going to need to show that we understand how it fits in an evolving landscape of prediction and forecasting. And so making sure that we're up to date and that we have the best information and we can place the observing system requirements in the context of an evolving prediction system is going to be important.
Okay, thank you.